Welcome to the new era of video creation with Biozy. This is our new series on teaching deep learning. Today we will discuss the image segmentation. Here are the contents. Image segmentation is the process of partitioning an image into multiple regions, or segments, to make the analysis of the image more manageable. The goal is to assign a label to every pixel in an image, which allows the machine to understand the content of the image at a pixel level. This is in contrast to simpler classification tasks, where a label is assigned to the entire image. Segmentation is crucial in several computer vision tasks, including object detection, identifying the boundaries of objects within an image, medical image analysis, delineating tumors, organs, or tissues in X-rays, CT scans, or MRIs, autonomous driving, segmenting the road, vehicles, pedestrians, and other important objects for decision-making. Image segmentation allows for more precise and granular information extraction, making it a fundamental task in computer vision. There are different types of image segmentation based on the level of detail required. Semantic segmentation. This is the most basic form of segmentation, where each pixel is assigned a label corresponding to a class, such as dog or tree. However, all instances of a class are treated the same. Instance segmentation. This builds on semantic segmentation by differentiating between distinct objects of the same class. For example, it can identify two separate dogs in an image, even though both belong to the same class. Panoptic segmentation. This combines both semantic and instance segmentation, providing both the semantic labels for each pixel and the instance-wise differentiation for objects. This is often used in complex environments like urban scenes or forests. The choice between these types of segmentation depends on the complexity of the task and the desired level of granularity. Image segmentation poses several challenges. Object variability. Objects in images vary greatly in shape, size, texture, and appearance due to factors like viewpoint, lighting conditions, and object deformation. This variability makes it difficult for algorithms to consistently segment objects. Occlusions and overlap. In many real-world scenarios, objects may overlap or be partially occluded, making it hard to distinguish boundaries between objects. Small object segmentation. Detecting and accurately segmenting small objects is another challenge. Small objects often have fewer pixels to work with, leading to lower accuracy in segmentation. Lighting and background variations. Segmentation models need to handle changes in lighting, shadows, and complex backgrounds, which can obscure object boundaries and make accurate segmentation harder. These challenges continue to drive research in segmentation algorithms, leading to more advanced techniques to address them. Before the rise of deep learning, image segmentation relied on traditional computer vision techniques. Some of the key approaches included thresholding, a simple method where pixel values above or below a certain threshold are segmented. This method is effective in cases where objects have well-defined intensity differences from the background. Edge detection. Algorithms like the canny edge detector used edges, sharp transitions in pixel intensity, to detect object boundaries. Region-based segmentation. This approach divides the image into regions based on some criterion, like pixel color or intensity homogeneity. Graph-based approaches. Methods like graph cuts represent the image as a graph and use optimization techniques to find the best segmentation boundary. These methods, while useful in simple or controlled environments, have limitations in handling complex scenes, noisy data, and large variations in object appearance. Convolutional neural networks, CNNs, have become the backbone of modern image segmentation. Unlike traditional methods, CNNs learn to automatically extract features from images, building hierarchical representations of objects at multiple scales. CNNs perform exceptionally well in tasks like semantic segmentation, where each pixel is labeled according to the class it belongs to. One of the strengths of CNNs is their ability to capture spatial hierarchies, starting with low-level features like edges, and gradually capturing more abstract features like textures, shapes, and objects. This allows CNNs to produce highly accurate segmentations, even in complex environments. The fully convolutional network, FCN, is an important architecture for semantic segmentation, which eliminates the fully connected layers of traditional CNNs and replaces them with convolutional layers that generate a pixel-wise classification map.
The UNet architecture, originally developed for biomedical image segmentation, has become one of the most popular models for image segmentation tasks. UNet features an encoder-decoder architecture, where the encoder extracts features through downsampling layers, and the decoder gradually upscales the feature maps back to the original image size. What sets UNet apart is its use of skip connections, which link corresponding layers in the encoder and decoder. These skip connections help preserve spatial information lost during downsampling and improve the model's ability to segment small or irregular objects with high accuracy. UNet is particularly well suited for medical imaging, where precise segmentation of small structures like tumors or organs is crucial. Mask RCNN extends the faster RCNN framework by adding a branch that predicts segmentation masks at the pixel level. This enables the model to perform instance segmentation, where not only the class, but also the precise boundaries of each object instance are predicted. Mask RCNN works by first generating region proposals using a region proposal network, RPN, followed by applying a row-I-align operation to extract features from the proposed regions. The model then predicts the class of each region, the bounding box of each object, a segmentation mask that indicates the exact boundary of each object instance. Mask RCNN has become one of the state-of-the-art methods for instance segmentation and works well in complex scenes with multiple objects. The DeepLab series of models, DeepLab V1, V2, V3, are designed to improve semantic segmentation by capturing more contextual information. One of the key innovations of DeepLab is the use of dilated convolutions. Traditional convolutions have a fixed receptive field, meaning they can only capture local information. Dilated convolutions increase the receptive field without losing spatial resolution, allowing the network to capture broader context and finer details, which is important for accurate segmentation. DeepLab also integrates conditional random fields, CRFs, as a post-processing step to refine the boundaries of segmentation, improving the accuracy of pixel-level predictions, particularly around object edges. DeepLab has achieved state-of-the-art performance on several semantic segmentation benchmarks, making it widely used in practical applications. Conditional random fields, CRFs, are often used as a post-processing technique to refine pixel-level segmentations. After a segmentation model generates an initial set of pixel labels, CRFs model the spatial dependencies between neighboring pixels to ensure smooth, coherent boundaries. CRFs work by assigning a probability to each possible segmentation configuration, considering both the local appearance, i.e., pixel intensities, and the relationships between neighboring pixels. The result is a more precise segmentation with well-defined object boundaries. When combined with deep learning models like DeepLab, CRFs can further enhance segmentation performance, especially in cases with intricate or fine boundaries.
Fully convolutional networks, FCNs, were one of the first deep learning models designed specifically for semantic segmentation. Unlike traditional CNNs, which have fully connected layers at the end, FCNs replace these with convolutional layers that generate a pixel-level classification map. FCNs enable end-to-end training of the segmentation model, where both feature extraction and segmentation are optimized together. The output is a segmentation map with the same spatial resolution as the input, allowing pixel-wise classification. FCNs marked a major breakthrough in semantic segmentation by leveraging the power of deep learning, enabling more accurate segmentation compared to traditional methods. Transfer learning is widely used in image segmentation to leverage pre-trained models on large, general-purpose datasets like ImageNet. These models have already learned useful features such as edges, textures, and shapes, which can be fine-tuned for specific segmentation tasks. In cases where labeled data is limited, Transfer learning helps overcome the challenge of training a segmentation model from scratch. By starting with a pre-trained model and fine-tuning it on a smaller dataset, transfer learning speeds up the learning process and leads to better performance, especially in domains like medical imaging, where annotated data is scarce. Image segmentation has a wide range of applications. Medical imaging. Segmentation is crucial in medical diagnostics for tasks such as tumor detection in MRI scans or organ segmentation in CT scans. Accurate segmentation of anatomical structures enables doctors to make more precise diagnoses and treatment plans. Autonomous vehicles. Segmentation allows self-driving cars to distinguish between the road, vehicles, pedestrians, and obstacles, enabling safer and more reliable navigation. Satellite imagery. In remote sensing, image segmentation is used to classify different land use types, such as forests, urban areas, and water bodies, aiding in environmental monitoring and urban planning. Augmented reality. In AR applications, segmentation helps separate the foreground, objects, from the background, enabling accurate overlay of digital content onto the real world. These examples illustrate the versatility of image segmentation across multiple industries. Looking ahead, several exciting trends are shaping the future of image segmentation. Multimodal integration. Future segmentation systems will increasingly combine visual data with other modalities, such as depth information, from LiDAR or stereo cameras, and audio. This can help improve segmentation performance in challenging environments like urban streets or indoor scenes. Few-shot learning. Few-shot learning approaches aim to enable segmentation models to perform well with very limited labeled data, which is especially important in specialized fields like medical imaging. Edge and mobile devices. With the rise of mobile computing and IoT, there is a growing demand for segmentation algorithms that run efficiently on edge devices like smartphones and embedded systems. This involves designing lightweight models that can perform real-time segmentation with limited computational resources. Complex scene handling. Further research is focusing on improving segmentation algorithms' ability to handle complex, cluttered environments, such as urban settings with overlapping objects and variable lighting. The future of image segmentation is likely to bring more robust and adaptable systems with real-time capabilities and enhanced performance across multiple domains. Image segmentation is a crucial task for enabling machines to understand images at a pixel level. Over the years, deep learning techniques like UNet, mask-RCNN, and DeepLab have revolutionized segmentation, offering unprecedented accuracy and versatility. While there are still challenges in dealing with small objects, occlusions, and real-time performance, ongoing research is making significant progress. The future of image segmentation promises to bring even more powerful and efficient models, capable of handling multimodal data and complex real-world environments. By addressing these challenges, we are opening the door to more intelligent systems that can better interact with and understand the world around them.